Hi all. For this lab, we're going to be playing around with a cellular automata algorithm based on a set of rules presented in a book by Stephen Wolfram called A New Kind of Science. First, we'll briefly discuss the book and some of the ideas presented by Stephen Wolfram. We'll then take a look at a row-by-row cellular automata algorithm, which we'll call Wolfram Pyramids, which is modified from one of the algorithms presented in the book. We'll then take a look at an example to see how the algorithm works, along with some interesting patterns generated by different rules, and when we're comfortable with the algorithm, we'll implement it for given rules. Finally, we'll discuss how the rules are named and how we can generalize the algorithm to work with a given arbitrary rule. It should be fun. Let's get started. Of course, Stephen Wolfram is one of the great geniuses of our time, and his projects include the symbolic mathematics software suite Mathematica and Wolfram Alpha, which was wowing us with natural language-based AI long before the rise of large language models. His book, A New Kind of Science, presents astonishing examples of how macroscopic complexity can emerge in unexpected ways from simple sets of microscopic rules, which he feels may fundamentally change the way we view the complexity we encounter in nature and life. Moreover, the book is freely available online and written in a way that is easily approachable, even for us regular monkeys, so I strongly recommend that you take a look at it when you have some time on your hands. In any case, today we're going to be playing around with one of the algorithms presented in A New Kind of Science, which has been slightly modified for this lab. The best way to see how the algorithm works is to dive straight into an example. We basically start with a large grid of cells that are initially all white except for one black cell, as shown in this slide, and a rule or set of mappings, as shown at the top. The rule is given a number by Wolfram, which we'll discuss in more detail later on in this presentation. In this example, we're dealing with rule number 3. Now, we can think of each cell in the grid as having 3 parents, which are the cells directly and diagonally above the cell, and 3 children, which are the cells directly and diagonally below the cell. For example, the cell shown in green here has these 3 cells as its parents, and these 3 cells as its children. Now, after we have set one cell to be black, we're going to consider each of its children cells. In other words, we're going to consider each of the cells highlighted in yellow here. The black cell's first child is shown as a question mark here, and the first child's parents are marked in red. We're then going to look at the pattern of markings in the child's 3 parents. In this case, the left parent is white, the parent directly above is white, and the right parent is black. We then look that pattern up in the rule mapping. When we do that, we find that the child associated with that pattern should be black. We thus paint the child black and move on to the next child. If we repeat the process for the next child, we see that the left parent is white, the parent directly above is black, and the right parent is white. So we look that pattern up in the mapping, and we see that the child with this pattern of parents should be white. So we leave the child white and move on to the last child. Similarly, for the last child, we see that the pattern among the parents is black, white, white. So we look this pattern up in the mappings and see that the child should be white. We've now gone through all the children of the original black parent, so we're ready to move on to the next row. Since we have updated 3 cells, we're now going to repeat the process on all the children of these 3 cells. In other words, we're going to consider all the cells highlighted in yellow here. The first of these cells has parental pattern white, white, black, so we look up this pattern in the mapping and see that the child should be black. The next child has parental pattern white, black, white, and if we look that pattern up, we see that this child should be white. Similarly, with parental pattern black, white, white, the next child should be white. The next child has 3 white parents and so should be black. And the last child should similarly be black. So now we have finished going through all the affected children in this row, and we're ready to move on to the next row. Again, we're going to consider all the children of the cells updated in the previous row, highlighted in yellow here, and we similarly repeat the process for these children. Let's speed it up a bit. And then, of course, we're again ready to move on to the next row. You get the idea. Let's let the algorithm continue for the remaining rows. We've only considered a few rows here, but the process can continue for an arbitrary number of rows. Now, if you take a look at a new kind of science, you might notice that the algorithm described here is slightly different than that described by Wolfram. Here, for each row, we only consider the children of cells that have been assigned a color in the previous row, whereas Wolfram originally applies the algorithm to all cells in each row starting from the second row. In many cases, the patterns generated are the same, but in many others, this isn't so. After you finish the lab, it might be interesting to compare the patterns you generate to those presented in the book. In any case, let's stick with rule 3 just a little longer, but zoom out a bit. We see that the pattern continues and we get an interesting pyramid-like image emerging. However, the most interesting thing happens when we start looking at the images generated by different rules. For example, this set of mappings is called Rule 30. We're going to apply the same algorithm as before, but using these mappings instead. Interesting, right? This time there doesn't appear to be a clear pattern in the generated image. It looks as though elements of pseudo-randomness have somehow been introduced. I say pseudo-random because of course the final pattern generated is completely determined by the rule, but it is certainly interesting how this level of macroscopic complexity emerged from a rule fundamentally as simple as the previous rule we looked at. Let's take a look at a couple of more examples. This mapping is called Rule 90. Again, we're going to run the same algorithm as before, but using this new set of mappings instead. Wow, this time a Sierpinski triangle-like fractal emerged. We have self-identity within the structure, a true fractal. Let's take a look at one more example. This final mapping we'll look at is called Rule 169, which generates my favorite Wolfram pyramid. Again, we'll run the same algorithm as before, but using this new set of mappings instead. This time, we don't end up with a pure fractal as we did in the previous example, but we certainly have a fractal-like structure reminiscent of the Mandelbrot set in some sense, with self-similarity somehow being introduced at different levels within the structure. Fascinating, right? Okay, let's return to the basic algorithm for generating a Wolfram pyramid. After we have created a grid of cells, the first step is to mark a cell in the first row as black. For convenience, it's a good idea to set up a wide grid with an odd width so that we can paint the cell at the center black and have some room to work with. Then, starting from the next row, we update all the cells that are children of the cells that have been updated in the previous row according to the pattern of markings in the children's parents and the respective mapping associated with the rule we're working with. We then repeat the process row by row until we have completed a desired number of rows. Great, so at this point you're ready to complete task 1, which is to manually color in cells on paper for given rules to make sure you understand the algorithm, and task 2, which is to implement the algorithm for a given rule in a programming language of your choice. The output image can be something like a PNG file or simply a pattern generated in the terminal or text file. So pause the video now, complete tasks 1 and 2, and then hit play again when you're ready to continue. Alright, now let's take a look at how the rules have been named. As we already noticed, the rules have been assigned numbers. For example, we have already explored rules 3, 30, 90, and 169. But how are the rules assigned numbers? Well, if we think about it, when we decide whether a cell should be painted black or white, we look at the color of each of its 3 parents. Since each of the parents could be either black or white, there are 2 to the power of 3, that is 8 possible cases that we might need to look up in the rule mapping. This is made clearer if we treat the parent cells as bits, with black parents having value 1 and white parents having value 0. In that case, each parent state could be assigned a 3-bit label from 0 to 7. We can think of these labels from 0 to 7 as keys or indices we can use to look up an action to be performed. Now, a given rule is simply a mapping to either black or white from each parent state. For example, here is a degenerate rule in which all possible parent states are mapped to the color white. This wouldn't result in an interesting pyramid. It would be completely white except for a black point at its apex, but it is one possible mapping. Another possible mapping is one in which all possible parent states are mapped to white except for the state where all parents are white. That's quite an easy rule to visualize. It would generate a pyramid made up of alternating black and white horizontal rows. Another mapping is one in which all possible parent states are mapped to white except for the states where the parents are white, white, black. Yet another mapping is one in which all possible parent states are mapped to white except for the states white, white, black, and white, white, white. And here are some more possible mappings. Now the question is, how many mappings are possible altogether? Think about it for a second. Of course, since there are 8 possible parent states, and each parent state is mapped to either black or white, there must be 2 to the power of 8 or 256 possible rules. This is even clearer if we treat each mapping as a sequence of 8 bits or a byte, in which case the rules can be assigned values from 0 to 255. And this is indeed the system of rule numbering that Wolfram uses. Now the problem becomes, given a byte that represents a rule, how can we determine whether a given child cell should be colored black or white? As before, we're going to have to look at the 3 parents of a given child. This time, however, we're going to treat each parent as a bit with value 0 if the parent is white, or 1 if the parent is black. To get which state the parents represent, we shift the left parent's bit left twice, the bit of the parent directly above left once, and we don't shift the bit of the right parent at all. We then join these bits either by adding or applying a logic OR operation to get the state label value from 0 to 7, which we can treat as a key or index to look up a bit in the rule byte. That is, now that we know the parent state value, we check the bit at that position in the rule byte using a logic AND operation. If the bit is 0, it means that the child should be colored white. If the bit is 1, it means the child should be colored black. And then we simply paint the child the appropriate color. Great. So now you're ready to move on to task 3, which is to implement a generalized algorithm that accepts a rule number as a byte and generates the respective pyramid. And task 4, which is to use your algorithm to identify some interesting pyramids and finally report on your results. And that's the lab overview. I hope you enjoyed the video. Have fun with the lab.